after having a broad overview on phase transformation and the important concept of a critical radius for phase transformations, let us look at melting of nanocrystals. We had noted that we have a well defined melting point Tm at which the entire lattice breaks, and therefore, you have a molten state, and this is unlike the freezing which we had talked about. On the other hand, when we talked about the melting point, it was the melting point of what is known as a bulk crystal or a large crystal. The melting point of a material is an indicator of the Bronze strength of the material, though the boiling point is a better reference as it is structure independent. In the solid state, for instance, you have various kind of phases possible like the BCC crystal or the FCC crystal, and this would affect the melting point, but boiling point is from the liquid state to the gaseous state, and that is a better indicator of the bond strength. But nevertheless, melting point also gives you some kind of an indication of what is the bond strength in a material. In bulk system, surface to volume ratio is small and curvature effects can be ignored. That essentially implies we can talk about a single number known as the bulk melting point. In nanocrystals, the number of surface atoms is considerable fraction of the total number of atoms, and these atoms, as we know, have got a higher energy and a higher degree of freedom, which means they have freedom of more vibration as compared to the atoms in the bulk. This implies, as a first intuitive guess, that surface atoms are expected to melt below the melting point of the bulk. So, though this is how much is it true, how much it does it stand to experimental results, we will have scrutiny, we will see in a moment, but as a first intuitive guess, we would expect that surface atoms, because of the higher energy they have got and the higher freedom they enjoy, they would tend to melt before the bulk atoms. And we have already noted that in 0D and 1D nanocrystals, curvature effects are important and cannot be ignored. Now, as the size of a freestanding nanocrystal is reduced below about, say for instance, about 100 nanometer, and I am talking about single crystals which are freestanding, it is noticed that its melting point is reduced with respect to the bulk melting point. In fact, experiments have shown that gold crystals about 10 nanometers in size melt about 100 degrees below the melting point of the bulk. So, there is a considerable depression in the melting point when you go to nanoscale and for that we really have to go to small sizes like about 10 nanometers, and the bulk melting point of gold happens to be 1064 degrees Celsius. Now, there is a continuum formula which exists, and we will though how correct is this formula or how accurate it is, we will ignore for now, and we will consider a formula in which the melting point of the surface is given with respect to the melting point of the bulk material. The formula goes as T surface melting is Tm into 1 minus 2 gamma solid liquid by delta Hf into R, where Tm is, as we noted, is the bulk melting point. The surface melting point, that means as if we are assuming now that the surface atoms are melting first, the gamma solid liquid is the solid liquid interfacial energy, and delta Hf is the enthalpy of fusion of the bulk material, and R is the radius of the particle. The important take home message from this formula is that if I reduce my size, that means if R decreases, then the surface Tm surface would decrease. That means that there will, because this is 1 minus this fraction, and therefore, you would notice that if I decrease my radius of the particle, which means also that curvature is going to increase, then I would note that the Tm surface would actually decrease. That means, the surface atoms would show a depression in the melting point with respect to the bulk melting point. Now, if I now track my melting point with vis-a-vis the radius of the particle, then of course, you have the bulk melting point, and this is some kind of a schematic drawn schematic trend line which is drawn for gold nanoparticles. Then we notice that there is a severe depression in the melting point as you reduce the size, and this starts to play a considerable role when the size of the particle is below about 50 nanometers. And we already noted that when the size is 10 nanometers, there is almost 100 degrees depression in the melting point. Now, this implies there are 2 points we have talked about, and these 2 points need to be resolved, and the first point we mentioned is that surface would tend to melt below the melting point of the bulk. This is point number 1, and we have a few more things to say regarding that, how true is it or how true it is not. Second thing, we are noticing an experimental result wherein you are noticing that actually the melting point of a nanocrystal, and now I am not differentiating the surface from the interior, I am assuming that the entire nanocrystal is melting, and this we are seeing there is a depression in the melting point of the nanocrystal. and this trend line which is seen for gold can also be observed for other materials like lead, copper, bismuth, silicon, and the trend lines are very similar. In other words, if you go below about 50 nanometer size, there is a depression in the melting point. Now, the question, obvious question which arises is that, is the surface melting first, and therefore, the next layer becomes a surface, then the next layer becomes a surface, or the next layer becomes, then therefore, there is a continuous melting from outward to inward. There are two possibilities. So, let me write down the scenario of melting. So, there is one possibility that the surface actually melts first. So, this layer gets molten, which means now the effective surface is moved inward, and this is the new surface, and which is even smaller in size, and since the temperature is already above the melting point of the surface, this crystal, it is definitely, this is going to be above the melting point of this crystal, and therefore, my melting would progress inward. This is scenario 1. The other possibility is that the entire crystal melts at a single temperature, and now I call it, of course, the Tm of the nanocrystal, which is now obviously a function of the radius r. Now, which of these two is true is a important question. Is it that the melting actually happens in the surface and progresses inward, or does the whole nanoparticle melt at a single temperature? And let us answer this question, that where does melting start first? A simple minded guess would be that the melting starts at the surface of the nanocrystal, as the formula I pointed out in the previous slide. But in actual experiments, and the one which I would like to cite now is by Wang et al., which is goes back to 1999, which they did on gold nanorods heated by a laser beam. They found that they could not differentiate the melting of the surface from the interior, and both the inside and of the nanocrystal and the surface seem to actually melt as a whole. Though more work has to be done on various systems and more careful experimentation has to reveal really does actually the surface melt before the interior, but as it stands today, the understanding seems to be that it is not a scenario 1 which is operative, but a scenario 2 wherein actually the whole nanocrystal melts at a single temperature, which is what you expect for the bulk crystal. In a bulk crystal, you define a melting point which is not surface, interior, etc. dependent. So, you expect that it is melting at a single temperature, though as I pointed out, more work has to be actually done to understand this phenomenon. Now, it is not always necessary that this nanocrystal need be a freestanding nanocrystal. Often this nanocrystal, it could be embedded in a matrix, like for instance, the way to produce lead nanocrystal is to actually melt spin. Melt spinning is a technique in which you actually take, you melt your lead and aluminum together and spin it in the form of a ribbon, and often you will get lead nanoparticles which are embedded in a matrix, and a schematic of such a system is shown here, wherein for instance, this lead is this lead could be this phase, which is the black phase, or and this could be the matrix, okay, which could be aluminum. So, in this system, the nanoparticles or the nanocrystals are not freestanding, but they are embedded in a matrix. In such a scenario, there is an extension of the concept we just now saw about melting, that it is now not purely, we cannot say that there is going to be a depression or an elevation in the melting point, both of which are possible. We will have to take it system by system. So, if the crystal is embedded in a matrix, its melting point may decrease or increase with respect to the bulk, depending on the relative magnitudes of the particle matrix, that means a crystal matrix, and liquid matrix interfacial energies. So, now if I know the relative magnitudes of these two, the crystal matrix and the liquid matrix interfacial energies, I can predict, will I have a depression in the melting point, or will there be something known as superheating, which is means an elevation in the melting point. Now, if gamma particle matrix is greater than the gamma liquid matrix, in other words, the gamma liquid matrix is the lower of the two interfacial energies, then formation of the interfacial liquid lowers the energy, it is obvious. Therefore, now suppose originally there was an unmolten state, in which case I had this particle in a matrix, and now the relevant interfacial energy is for the solid with the liquid, which is gamma solid or particle matrix. Now, if instead of this thing melts, this region of space melts, then I will have to replace it with this quantity, which is now this is a molten state, in which case I can replace this by gamma liquid matrix. and since gamma liquid matrix is lower in energy, it would rather melt at a lower, so to overall reduce the energy of the system, and that means there will be a depression in the melting point. The opposite would be true if the gamma particle matrix is lower than the gamma liquid matrix. In such a case, you would observe an elevation in melting point, which is called superheating, and the embedded crystal will melt above its bulk melting point. And this is observed in an example of aluminum indium alloy matrix. So, suppose you had aluminum indium particles in an aluminum alloy matrix, then you would actually observe an elevation in melting point, which is called superheating. So, just to summarize the slides related to melting, we observe that if you have freestanding nanocrystals, then there is a depression in the melting point, which could be a large fraction of the overall melting point. For instance, if 100 degrees depression would imply that there is about 10% reduction in melting point if you reduce the crystal size to about 10 nanometer. Second thing we noticed is that as the understanding stands today, that the entire nanoparticle melts at a single temperature rather than the surface inward melting, which could also be a possibility which needs to be explored. Now, and the third thing we noticed was that if I have this nanocrystal not as a free nanocrystal, but as embedded in a matrix, then there could be an elevation in the melting point, or there could be a depression in the melting point. That depends on the relative interfacial energies between the solid and the liquid, or the crystal and the matrix. Now, let us take up the example of solid to solid phase transformation in nanocrystals, and we already noticed that when you are talking about for instance liquid to solid or a solid to liquid phase transformation, then I can ignore something known as the strain energy. But when you talk about solid to solid phase transformation, still the concept of an R star is valid, but in the calculation of R star I need to invoke the strain energy term as well. That is what we had noted before. Phase transformations in nanocrystals is expected to be different from bulk materials. So, this is very obvious, and we will see why it is obvious very soon. Heterogeneous nucleation at the surface is expected to play a dominant role due to its proximity. So far we said that suppose I am doing a melt solidification experiment, and suppose I do this experiment for instance in a containerless method, that means I have no container, there is no wall, then I can reasonably expect that homogeneous nucleation is going to take place. But in a solid to solid phase transformation, it is heterogeneous nucleation which is going to be a dominant form of nucleation, because you cannot avoid defects in a material, like there are going to be grain boundaries, there are going to be stacking faults, there are going to be dislocations, and even enriched regions of vacancies have known to be are known to play a role in heterogeneous nucleation. So, heterogeneous and in the case of nanoparticles, there is one defect which is very close to the bulk of the material, which is the surface, and therefore surface is expected to play an important role in heterogeneous nucleation in nanocrystals, or heterogeneous nucleation leading to a phase transformation in nanocrystals. Additionally, we also expect that the activation energies for phase transformation is expected to be different from the bulk, which is not an unreasonable expectation. Additionally, apart from the thermodynamic aspects, we also would notice that the kinetics of phase transformation is expected to be highly enhanced with respect to the bulk. And the reason obvious, we list the three reasons, important reasons, that smaller length scale for diffusion involved. And suppose I am talking about a diffusional transformation for now, like we have been doing so far, the first order diffusional transformation, which produced by nucleation, which progress by nucleation and growth, then I would notice that since the overall particle size is very small, the overall length scale for diffusion for phase transformation to be completed is going to be small. It is also going to be order of nanoscale. Then there are going to be other effects like surface diffusion, which are going to play a prominent role, because now the entire material is dominated by surface. Then the third important point is that there is going to be lesser constraint on the system. We had noted that previously by drawing some schematics, that how if I take a region out of a material and it transforms to a different volume, then I have to refit that material into the bulk of the material, which is going to give rise to strain energy. But suppose the system is very small, then the free surfaces can actually relax, and therefore the system is less constrained. That implies that phase transformation typically involve volume changes, and since the amount of constraining material is less, the transformed volume stresses caused by the transformation are lower, and that means that there is going to be less impediment to the phase transformation, and we had noted earlier that actually out of the 3 terms energies involved in a phase transformation, the interfacial energy and the strain energy term tends to oppose the phase transformation, and since now the system is less constrained, that means if there is a volume change or a shape change, this can easily be accommodated because there is a free surface in proximity, and that implies that typically the strain energy term is going to be a lower term in a nanocrystal transformation as compared to a bulk transformation. So, let us understand this. Now, suppose I have a bulk crystal and I have a certain region which is transforming, and assume that after transformation this volume becomes like this. That means, there is a shape change and there is a volume change. Now, in the case of the bulk, this transformed volume has to be reinserted into this volume, and therefore, there is going to be a lot of strain energy term. In the case of a nanocrystal, there is no surrounding medium, therefore, this transformation can proceed with lesser constraint, and therefore, and additionally we have already noted that suppose there can be surface diffusion dominance, there can also be the overall length scale for diffusion for this could be small, and therefore, even if it is a diffusional transformation or a diffusionless shear transformation, the overall expectation is that the strain energy term is going to be a small term, and many times we may like to ignore the strain energy term in the phase transformation. Now, we have already noted many times before that in bulk materials multiple nucleation events are necessary, and we all characterize nucleation as nucleation rate, that means number of nuclei forming per unit time per unit volume, and that is what leads to phase transformation. So, suppose and a schematic is shown here for that. So, you have a region of material wherein there are certain nuclei which form the black dots, and with time these nuclei grow, and as these nuclei grow, fresh nuclei are formed in different regions, and finally, the entire volume is transformed. So, the new transformed volume. So, it actually should be shaded black. So, maybe it is a good idea to shade the whole region black, because now this is the transformed volume which is now the black material. Okay. Now, in the case of nanocrystals, the size of the transformation nucleus may become comparable to the volume of material, and when we talked about this R star, the critical size for nucleus, we noted that it is of the order of 1 to 10 nanometer, it is of the order of the nanoscale. Okay. And therefore, a single nucleation event may lead to a solid to solid phase transformation in a nanocrystal, which is very different from the case of a bulk crystal. And the schematic is shown here, that you have a nanocrystal at the bottom which is shown by A, and I assume that the nanocrystal is of the order of nanometers, then a single nucleation event is as good as transforming the entire material, and therefore, the transformed material is shown on the right. There have been some good research work, and this has typically been done on materials like CDSC and CDS, which are semiconductors, and the particle size range of 2.3 to 4.3 nanometers shows that for pressure induced transformation, and now this is not that usual heating transformation, but pressure induced transformation, it is seen that for a transformation from the woodsite to the rock salt structure, woodsite happens to be a ZNO type of structure, which is an hexagonal kind of a structure which has an A and C parameters as given here. On the other hand, the rock salt structure is a familiar NaCl type structure which is cubic, and you can notice here that the woodsite structure has a higher volume per motif as compared to the rock salt structure. That means, if I increase the pressure, the tendency would be to actually convert this woodsite to rock salt, and this pressure typically is of the order of gigapascals, and if you apply 3 gigapascal, it is seen that a single nucleation event can lead to the transformation of the whole volume. And that implies that this situation is very different from that of a bulk crystal, wherein nucleation alone does not lead to transformation, there has to be nucleation followed by growth. Now, of course, there has to be a transition from the nucleation event to single nucleation event to a bulk system, wherein there is multiple nucleation events, and the transition occurs via what is known as a single nucleation followed by growth regime. So, now I can divide my size regimes into 3 parts. One is this very small regime of the order of 2 nanometers, one intermediate size regime of the order of 10 nanometers or maybe 10 to 15. Of course, this depends on system to system, and in this case of course, I am taking the example of CDSE or CDS crystals, and therefore, if I change the system, these numbers would be different. And the third is the bulk, which is now when I am talking about bulk, it could be more than about 100 nanometers or 500 nanometers, which I call a bulk system. In the small nanoscale regime, I notice that this 2 nanometer is of the same order of magnitude as the R star, my critical nucleation radius. So, this is of the order of critical nucleation radius, and therefore, a single nucleation event can lead to phase transformation. In this intermediate size particles like about 10 nanometer particles, we notice that single nucleation can lead to a phase transformation, but there needs to be a certain growth, because the nucleus size, as you can see here as indicated by this black, is actually smaller than the particle, but then there is not sufficient region around it for a second nucleus to form, with that means given a small size, and therefore, this nucleus grows, leading to a complete phase transformation. And finally, of course, you have the bulk, wherein which is, as I told you, could be of the order of 100 nanometers or more, multiple nucleation events followed by growth, which is the usual mechanism for bulk crystals. Now, further if you look at closely at the 2 nanometer size crystals, which is you can see was a reason for, or in the same region as the experimental study, which is from 2.3 to 4.3 nanometers, you notice that you can subdivide this region into very small sizes, which wherein the nucleation event is interface controlled, that means surface controlled, and you can talk about what you might call a volume control regime, which is slightly bigger than those very small volumes. So, let me summarize this very important slide. Since R star, which is the critical nucleation radius, is of the order of nanometers, usually typically 1 nanometer or to say maybe 10 nanometers. In some systems, let us assume a system like CDSE or CDS, wherein it is of the order of 1 nanometer, then a single nucleation event can lead to a phase transformation, which is unlike the bulk crystals. Now, the important work on CDSE has been done on this pressure induced transformation, and the pressure for transformation is pretty high, of the order of gigapascals. We are talking about a phase transformation from the Woodside structure to the rock salt structure. That means, from an hexagonal structure, it is going to a cubic structure, and that since it is pressure induced transformation, we expect that there is going to be a reduction in volume of the unit cell, which is what is seen here from the volume of the unit cells. And in such a system, we see that in small scales, a single nucleation event is enough to cause the entire transformation of the volume. Now, nucleation could occur in the bulk or on the surface, and the activation energy for the transformation is seen to increase with size regime size considered. So, if you are talking about the experiments conducted in CDSE and CDS, and you are talking about these nanoscale particles, then the activation energy for the transformation is seen to increase with size. At larger crystallized sizes, single nucleation event is followed by growth of transformation to be complete, which we noted before. Additionally, we note that smaller crystallites require higher pressure for transformation, and this, for this particular case, we will see more examples, and we will see one more example, wherein we will actually note the pressure at which smaller crystals transform as compared to larger crystals, both being in the nanoscale. Another example we consider here, and here we are taking up some illustrative examples, but much of this can the concepts can actually be applied across very many systems, including metallic systems and other systems. In silicon, and now we are talking about SiO2 coated silicon, pressure induced transformation from diamond cubic to primitive hexagonal structure, it is seen that crystals as large as 50 nanometers transform by a single nucleation event. So, here we noted that for instance, that it is about of the order of 2 nanometers that be a single about 10 nanometers, sorry, of the order of 10 nanometers that a single nucleation event is responsible, but in other systems this size can be as long as 50 nanometers, and this also tells us that the concept is applicable to broader class of systems, and in this case we have to especially note that it is not a freestanding silicon crystal, but it is some kind of a core shell structure where silicon is coated with SiO2, and this is a natural, can be also thought of as a natural consequence of the oxidation of the silicon crystal. And as expected, the shape of the crystals change on phase transformation, and this is of course a homogeneous deformation we are talking about. And bulk behavior in this case of the silicon is expected to take over after about 100 nanometers. So, it is clear that when you study more than one size system, that up to about 50 nanometers seems to be the regime where you can actually have A single nucleation event, of course, it could be nucleation followed by growth, but a single nucleation event is responsible for the entire phase transformation. And when you go to for instance, about 100 nanometer or more, we can assume that it is bulk like behavior with respect to what you might call the phase transformation by nucleation and growth. So, now we are taking more and more examples, we are seeing more and more examples, and we had asked, and very early in the course we had asked a question that what is bulk. So, now with respect to nucleation and phase transformation, we can see that a 100 nanometer crystal can be called bulk, even though we know it is a nanoscale crystal, because in terms of the mechanism for phase transformation, it is no different from a bulk crystal, or it is not very different from a bulk crystal, because now you have multiple nucleation events followed by growth. So, I can call it bulk like, even though it is still in the nanoscale. Another example of a solid to solid phase transformation which has been studied is the transformation from gamma Fe2O3 to alpha Fe2O3. Again, this is pressure induced phase transformation, and this gamma Fe2O3 is actually a metastable form at room temperature with respect to the alpha form. This is a cubic form and its volume of the unit cell is about 0.58. The alpha form, and which is a smaller unit cell, is actually a rhombohedral crystal, and it has got A and C parameters as A equal to 0.504 and C is 1.37, is an alumina form of a crystal. So, you have two forms, one with a larger unit cell, one with a smaller unit cell, and this transformation, as you can perhaps you can guess, that can be driven by pressure. And the important thing to note is that as you decrease the size, and now we are really in the very small scale regime, 7 nanometer to 5 nanometer to 3 nanometer, you can see that the transformation pressure actually increases. That means, for smaller and smaller particles, actually you need larger and larger pressures for phase transformation to take place. And of course, these pressures are employed by using a diamond anvil, and so there are inherent complications in actually studying the in situ phase transformation and getting the signal of how the transformation has taken place. So, these are very careful experiments which have to be conducted, but the general trend line seems to be that as you reduce the crystallite size, you need to apply more and more pressure for phase transformation to take place. Next, we take up a couple of more physical properties, and both of these are actually vast areas of research wherein a lot of work has been done, but we will take a small sample of results to understand that how nanomaterials can actually be different from bulk materials. And as usual, we take up those examples where the demarcation is very clear cut, and often there is a startling or a very different kind of a variation as compared to the bulk, so that we can understand that at the nanoscale there are some very interesting effects which we do not observe in the bulk materials. So, let us one of those physical properties we talk about now next is that thermal conductivity. We know that thermal conduction occurs due to electrons and phonons. In normal metallic materials, electrons are the dominant form of conduction, but suppose I am talking about a diamond, we know that diamond has no free electrons, and therefore, or very little free electrons at room temperature. Therefore, it is phonons which are responsible for thermal conduction. Actually, diamond happens to be a very good thermal conductor. In fact, if one holds a diamond blade and actually cuts through ice, the heat of the hand can actually be conducted very nicely through the diamond, and it will actually cut ice very nicely. And this phononic mode of conduction, as you know, phonons are quantized normal modes of lattice vibrations, and later on we will talk about plasmons in the context of optical properties. Plasmons are collective oscillations of electrons, while phonons are collective oscillations of quantized oscillations of elastic oscillations of atoms, or we may call lattice vibrations. In nanomaterials, the phonon wavelength can be comparable to the length scale of the microstructure, or in the case a nanoparticle itself. Okay. So, this is an important point. That means, phonons can get confined in the material because now it cannot travel through the medium. So, that is an important point to note, and therefore, you do expect that when phononic conduction is the dominant form of conduction, that in nanoscale materials things are going to be very different. Even in cases where electronic conduction is the important mechanism, you do expect that it is going to be different from the normal materials. Now, if you talk about phonon wavelength, you can write down E phonon is h v by lambda. V is the velocity of sound, and the momentum of photon h by lambda. Putting together, we can see the lambda phonon is of the order of 10 power minus 10, or in some cases you can talk about it of the being in the nanoscale. Now, in experiments, there are at least two experiments we will take up. and or two results we will summarize here, and both of these results are, you might say, opposite sides of the whole spectrum. One is the case of carbon nanotubes, where you see an highly enhanced thermal conductivity which is occurring because of phonons, and in fact you observe something like about 3000 watt per meter per Kelvin, which is 7 times or more than that for copper, and this is observed in carbon nanotubes along the length, and this is expected to be because of the phononic mechanism. Now, we later on, when we talk about conduction, electrical conduction, we will also notice that in carbon nanotubes you can actually have electrical transport which is ballistic. Again, that means unimpeded transport of electrons across the length of the carbon nanotube, which means that you can have ballistic conduction. So, you can see the thermal conductivities and electronic conductivities along carbon nanotubes is very high, and the result which is contrary to that we are also talking about, which we will take up now, is the case of nano size platinum films, and we are talking about in plane conductivity and its dependence on thickness. So, we have two examples in front of us. One is the case of the carbon nanotube, wherein phononic conductivity is giving us very high conductivity as compared to even that of copper along the length of the tube. The other case is the case of platinum, where you expect free electrons to be present, and we notice that the in plane conductivity of these thin films, these are platinum thin films, actually decreased with size. Now, suppose I am talking about thermal conductivity and its plot with temperature, then you notice that for platinum bulk, that the thermal conductivity actually decreases with temperature, which is the normal behavior you would observe, because now you are going to have more and more collisions of electrons with phonons, and therefore, you actually would have a decreased mean free path, and therefore, you expect that the resistance of the material is going to actually increase, which is the case of electrical conductivity, and similarly you would also notice that the thermal conductivity is actually going to degrade with temperature. So, the thermal conductivity and electric conductivity both you expect to degrade with temperature, and which is what you see in the case of the platinum bulk. Now, if you talk about in plane thermal conductivity of platinum thin films, there are two important things to be noticed, which are both of which are unexpected and startling in some sense. Number one is that the overall conductivity value for any given temperature actually is much lower. So, you can see that a 28 nanometer film, the conductivity, for instance, you take at temperature like 120 Kelvin, you notice that it is about 20 and this is slightly less than 80. So, there is a considerable reduction in the thermal conductivity at any given temperature, and here even at a higher temperature 300 Kelvin, you notice this is about 30 and this is about 70. So, it is more than double or 2.5 times reduced with respect to the bulk value. Further, you also noticed if the film size is made thinner, then the thermal conductivity actually decreases even more. That means, a 15 nanometer film is actually having a lower thermal conductivity as compared to a 28 nanometer film, which is having a lower thermal conductivity as compared to the bulk. So, therefore, you keep on increasing the thickness, at some point of time I would perhaps have a transition from what you might call the nanoscale regime to the bulk regime. Now, there is another important effect which you see from the curve, which is very different from that of the bulk, and this is seen in the regime of 70 to about 340 Kelvin, which is a regime in which the experimentation was done in the platinum films. And you can notice that in this regime actually the thermal conductivity increases with temperature. In the case of the bulk semiconductor, you already noticed that the thermal conductivity decreases with temperature, but unlike the bulk, for the nano size films, the thermal conductivity actually increased with temperature. So, the true startling effects in the case of materials having electronic conductivity, number one is that the thermal conductivity actually increased with temperature in the nanoscale materials, and number two, the thermal conductivity of the nanoscale material, and I am talking about in plane conductivity of films, and this is not nanoparticles, this is not nanotubes, but actually films, and this films is much lower than the bulk counterparts. And this is in contrast with a nanostructure like carbon nanotube, wherein you actually observe much higher or a highly enhanced thermal conductivity along the length of a carbon nanotube. So, though we have only considered a very little part of the whole story of the thermal conductivity, but this I hope can convey the what you call important message that the thermal conductivity of nanomaterials is going to be very, very different from that of the bulk materials, and this may have important consequences when you are actually designing devices and you are worried about the cooling of these devices, because there is a lot of heat generated because of, and you may want to put design various strategies for the cooling purposes, and you will notice that the cooling rate or the dissipation of heat through these some of these, for instance nanostructures, is going to be very different from that of the bulk, and therefore, that aspect has to be kept in mind when devices are designed. The next property, which perhaps is in some sense is very much related to the other properties we have been seeing before, which is related to the surface property, okay. Because in some sense the conduction we were talking about is more dominant by the bulk and rather than the surface, but in catalysis it is clear that it is a surface effect which is very, very important, and we know what is a catalyst. A catalyst is something which enhances the rate of the reaction, but it itself does not get consumed by the reaction. So, that is an important thing about the catalyst, that it itself does not get consumed, and you know a lot of industries rely upon good catalysts for industrial production, and catalysts are known to play an important role in reactions like oxidation of hydrogen, hydrogenation of hydrocarbons, oxidation of carbon monoxide, polypropylene epioxidation, etc. Again, like before, we will view this from a slightly classical viewpoint, and also we will take up only a couple of examples which are startling, while the literature on this area is again extremely vast, and it as because of the industrial application, this is also very, very useful to study catalysis, and especially the role of nanoparticles and nanocrystals in catalysis. If you look at the history of the material, only about 12 metals, and these typically belong to groups 8 and 1b, which are elemental catalysts. So, there are very small representation of the whole element periodic table which are naturally catalysts. Most widely used ones of those are 3D metals like iron, cobalt, nickel, copper, 4D metals like rhenium, palladium, silver, and 5D metals like platinum. So, these are some of the usually used catalysts for these some of these reactions which we have seen before. Copper is used in the catalysis of methanol production by hydrogenation of carbon monoxide, and silver is used in the production of ethylene oxide by the reaction of ethylene with oxygen. So, there are some examples. Now, how does this catalytic activity come in? So, again we go back a little back in time perhaps and take a classical viewpoint and try to understand this, that group 8 metals owe their catalytic activity to an optimum vacancy in the D band, like nickel and palladium, they have some kind of an optimum vacancy in the D band, and therefore, these group 8 metals have, you expect them to be having some catalytic activity. On the other hand, if you look at copper, silver and gold, they have a completely filled D band, but by the virtue that they have a low ionization potential and they can lose electrons from the D band, these can also function as catalysts in bulk form. So, therefore, either you need to have an vacancy in the D band, or if you have a low ionization potential, then you expect that such a material would be able to perform the role of a catalyst, and this reaction we could be talking about is the example of ethylene reaction, ethylene oxygen production ethylene oxide, or hydrogenation of carbon monoxide, etc. Gold, if you look at, gold does not satisfy any of these criteria, and it has a high ionization potential like 9.23, and therefore, you expect gold to perform poorly as a catalyst in bulk form. So, classically in bulk form, if you see gold, then you would say a gold is not going to be a catalyst, and therefore, I would discard it in the bulk form to play the role of a catalyst. Instead of talking about bulk crystals, suppose I am talking about nanoparticles, then it is obvious that nanoparticles are expected to have a certain better catalytic property as compared to bulk materials, and this comes from two obvious effects. One is the increase in surface area per unit volume, and the increase in surface activity to a high degree of unsaturated bonds. So, we do expect already that when you go to the nanoscale, there will be a certain benefit in using a catalyst in the nanocrystalline or nano form. Now, we just noted that gold actually does not perform good when you are talking about a bulk gold, but then it has been found that gold can actually be used as a catalyst in the nano form. So, gold has a high ionization potential, thus giving it poor affinity for molecular hydrogen and oxygen, and expected to perform poorly as a catalyst for hydrogenation and oxidation reaction under ambient conditions. Of course, it should be noted that the poor catalytic activity is for smooth gold surfaces at low temperatures. So, this is what we are referring to, and the expectation is that gold is not a very good catalyst. and it is very surprising that gold can perform the role of a catalyst in nanoform. Gold displays a drastic change in behavior and reduction of size. Gold nanoparticles supported on substrates like Fe2O3 and NiO can be used as a catalyst for CO oxidation even at low temperatures like 473 degrees Celsius. So, the observation is that now gold, which is not a bulk catalyst, can actually be used as a catalyst in nanoform, and needless to say, we have already noted before that these gold nanoparticles cannot be kept in touch with each other, then they will tend to coagulate. Therefore, they are typically embedded in a substrate, and these substrates have noted to be Fe2O3 and NiO, and we will note shortly the relevance and the importance of the substrate in this whole process. But the important thing to note is that gold now in nanoform can be used as a catalyst, and this is a very startling expectation or startling behavior. Factors which play an important role in catalytic properties of gold are, first of course, when you are talking about gold nanoparticles, size, that means size and size distribution and shape of the gold nanoparticle, and additionally, which is the important point, is the substrate. That means, what is the type of the support, what is the interface with the support substrate which is having, all these plays an important role in final outcome of the gold nanoparticles catalytic behavior. We already noted that gold nanoparticle melts at lower temperatures as compared to bulk materials. For instance, we have noted that 5 nanometer gold actually melts 200 degrees below the melting point, and this enhances the coagulation tendency, and nanoparticles are left in contact. And we have also noted that actually nanoparticles can sinter at temperatures much lower than, and we have noted the role of vacancies in this process of sintering, and therefore, we cannot leave these gold nanoparticles in touch with each other, they have to be isolated, and the substrate therefore performs the first important role of isolating these gold nanoparticles. But the important thing which comes out of the study, which the experimental study, is that there are additional benefits with respect to catalysis of using the substrate, and we have noticed two substrates we noted before, Fe2O3 and NiO. Now, when I embed a gold nanoparticle in a substrate, there are important parameters which automatically come about. What is of course the shape of the gold nanoparticle? Is the embedding partial like this picture on the right, or is it more like this, wherein the particle is not embedded deep into the substrate? So, we could have a range of embeddings. So, if I have a substrate, so my gold nanoparticle could be embedded such that only a small part of it is embedded. It could be such that it is almost like a semicircle, or it could be even deeper embedded. And what is the difference between all these? Of course, it is of course the surface area of gold which is exposed, which is going to be this number, this area, and you can see that the surface area of gold is actually decreasing as you go from a small embedding to a large embedding. Additionally, there is one more parameter to be noted in this embedding, and that is the interface. Suppose I look at the 3-dimensional figure of this, I can actually notice that when I have a particle which is embedded, then I would have actually a circular interface, which is the line of contact between the particle and the substrate. So, this area interface or a triple point length, which is the interface between the gold nanoparticle, the substrate and air, and that length would change depending on the embedding. So, in this case the length is small, in this case it is the maximum possible, and in this case there is somewhat intermediate length of embedding. That means, now the triple line which is passing as the interface between the 3 phases, that is also changing depending on the embedding. Now, this has important consequence on the catalysis, and we will note that by reading this phrase here. The substrate used in as support in the gold nanoparticle plays a profound role in catalytic properties of the system. First of all, the substrate determines the contact angle with which the gold nanoparticles make with the substrate, and which is of course size dependent. Gold and titania, 2 nanometer particles tended to wet the surface, while larger particles 5 nanometer have a contact angle of 90 degrees. That means 90 degree means partial wetting, and in the case of 2 nanometer particles, which is extremely small particles, they tend to form a uniform coverage. That means there is a wetting tendency. So, the wetting tendency itself is a function of the size of the nanoparticle. This wetting also is going to tell you what is the amount of interface that the gold nanoparticles will have with the substrate, which in turn plays a profound role in the catalysis. Hemispherical particles with more interface perimeter show higher catalytic efficiency than spherical particles attached to the substrate. So, if you compare the two pictures which are drawn here schematically below, one is the case of the non-wetting kind of a situation where the particle is sitting virtually outside versus a case of a 90-degree contact angle, which wherein the perimeter area is large, then you notice that the one which is embedded nicely is the one, or an hemispherical cap kind of a embedding is actually giving you a higher catalytic activity as compared to the one which is not wetting the surface. It is understood that the reacting species adsorb on the surface and interface defects like ledges, kinks and interface lines. So, interface lines play an important role apart from ledges and kinks which anyhow exist on the gold surface in determining the catalytic activity. At room temperature and low temperatures about less than 300 Kelvin, gold nanoparticles beat platinum and palladium hands down by 4 orders of magnitude in their catalytic activity. If you go back and look at this slide where we have talked about catalyst, we have noted that platinum and gold are well known catalysts. Platinum and palladium are well known catalysts, but gold we said in bulk form is not a catalyst. But when you go to nanoscale, it looks like the roles are reversed, and you can actually note that gold can outperform platinum palladium, of course in a certain regime of temperature, certain regime of embedding, that it can actually go and beat platinum and palladium with respect to the catalytic activity. And here we are talking about, of course, as I said, a limited regime where the cobalt carbon monoxide oxidation reaction has been studied, and this is understood due to the low activation energy of about 30 kilojoule per mole for use by using gold nanocrystals. Therefore, we see that when you go to the nanoscale, there are behaviors which are highly unexpected, and this continues to be so in the case of catalysis, where in spite of gold not being in the list of the usual known catalysts like the 3D metals like and the 4D metals and 5D metals like platinum, palladium, silver, cobalt, but we find that when you go to the nanoscale, and especially when we are trying to track catalytic activity of gold nanoparticles in the low temperature regime, and for a particular reaction like carbon monoxide, you can actually go ahead and beat some of the well known catalysts. And the important parameters, of course, in this whole thing is, of course, shape of the gold nanoparticles, the size of the gold nanoparticles, the substrate medium, is it titania or is it nickel oxide or is it one of the other materials which can be chosen as substrate material, the contact angle that gold nanoparticles makes with the substrate, and all this put together, it can be seen that there is an effective role that gold in nanoscale can actually perform in the case of catalysis, and this is again one of those startling effects which you see only when you go to the nanoscale. The next chapter we take up is related to the mechanical behavior of nanomaterials, and since defect structure plays a very important role in the mechanical behavior, we first talk about the defect structure followed by the mechanical behavior of nanomaterials. The defect structure in nanomaterials can be highly altered with respect to bulk materials, and this actually plays a direct role in terms of the properties, and these properties could be conductivity, diffusion, could be you could be even talking about compressive strength or fracture toughness, any one of those properties, and therefore I need to know the defect structure of nanomaterials, and we have already previously defined what does the term defect structure means. It includes, as we have noted before, entities like distribution of defects, its size, its overall volume fraction, etc., or length per unit volume, etc. So, we need to know the defect structure in a material, so that I can understand the profound differences in mechanical behavior of nanomaterials as compared to bulk materials. So, the first of these defects I take up is vacancies. We have already talked about vacancies in the context of diffusion, in the context of sintering of nanoparticles, and we have noted that depending on the curvature of the nanoparticle, is it going to be convex or concave, we have noted that there can be actually an enhancement in the vacancies, or there can be a depression in the equilibrium concentration of vacancies. And we have noted this, we will briefly revise what we mean by the equilibrium concentration of vacancies. We have noted that they are equilibrium thermodynamic defects, and suppose for now I will restrict myself to metals wherein there is no charge involved and the arguments can be simplistic made. We know that it costs enthalpy because there are broken bonds when you have a vacancy in a crystal, that it costs enthalpy in terms of putting a vacancy. But we also know that there is a configurational benefit when you have a vacancy. That means that when you are trying to minimize Gibbs free energy, which is given by delta G is equal to delta H minus T delta S, and for now I am restricting myself to configurational entropy, then I can note that there will be an offset because of this configurational entropy a certain temperature, at each temperature there will be an equilibrium concentration of vacancies. That means that if I am talking about the Gibbs free energy versus vacancy concentration, then I would notice that there initially will be a depression when I increase my temperature, but there will be at a given temperature, of course, there will be when I increase the number of vacancies, then there will be a depression in the Gibbs free energy, but after the equilibrium concentration, then there will be an increase in the Gibbs free energy again. That means the energy minima appears for only a certain number of vacancies. Now, of course, when you increase the temperature, then you will have an increased concentration of vacancies, and you go even further high temperature, there will be an increased concentration of vacancies, and close to the melting point in FCC metals like gold, silver and copper, the fraction of vacancies which is given by this formula NV by N is, which is depends goes as exponential of minus delta H by KT, is about 10 power minus 4. 1 in 10,000 of the lattice sites go missing close to the melting point in these metals. And as I pointed out, that as you increase the temperature, the fraction of vacancies keeps on increasing, and therefore, if I take any bulk material and I am talking about any finite temperature like about 300 Kelvin, then I expect an equilibrium concentration of vacancies. Now, what happens in nanocrystals? That is the question we are asking. In freestanding nanocrystals below a critical size, the benefit in configurational entropy does not offset the energy cost of introduction of vacancy, because now it is a nanocrystal, the number of sites over which this vacancy can configure are smaller, and this implies below a critical size you expect that vacancies may become thermodynamically unstable. Though this critical size we can call DC, the crystal can become free of vacancies. Of course, if you start from a high temperature and go to low temperature, the kinetics have to permit for these vacancies to escape. Now, for aluminum at 900 degrees Celsius with an activation energy of 0.66 eV, the critical size of the order of about 6 nanometers. That means, aluminum crystals below 6 nanometers will be free of vacancies. That means, such a crystal will have no equilibrium concentration, or vacancies will not be in thermodynamic equilibrium if put in such a crystal. Copper with a higher energy for formation of vacancy of about 1.29 electron volts, the critical size happens to be higher of about 86 nanometers. Now, the important point to note in this whole argument is that normally when you talk about configurational entropy, you are talking about Gibbs free energy, we are talking about what is known as bulk thermodynamics. That means, and these configurational entropy comes from statistical physics, which implies that I am talking about a large ensemble, which means about a mole of atoms or more, which are being sites which are being configured. But in nanocrystals, obviously the size of the system is limited, and the important question which arises, can I use bulk thermodynamics for calculation of quantities in these nanocrystals? The answer is obviously no, but it has been found that if you apply bulk statistical thermodynamics to even 100 nanometer crystals, so it is found approximately true that the results are reliable, but if you go down to very small sizes like about 6 nanometers, then the classical formulae cannot be used and they need to be modified for nanocrystals. Since we are not dealing in detail about the thermodynamics of nanoscale systems, but this important effect, though the calculation based on this may be 6 nanometer, could be erroneous, but the important thing is that when you go down to small scale system, we do expect that the system will become spontaneously free of vacancies. In other words, the system will not support vacancies as a stable thermodynamic defect, which is what is the case for the case of bulk crystals. Later on we will see, when we talk about dislocations also, that when you go to nanoscale, the system can actually become spontaneously free of dislocations. But in the case, the important difference between a dislocation and a vacancy being that in the case of a vacancy can be a thermodynamic defect in bulk, which or is a thermodynamic defect in bulk. That means, it is thermodynamically stable defect, but dislocation is not a thermodynamic defect, that means it is not stable in bulk, but in nanoscale the kinetics become such that it can actually move out of the crystal. So, there are important differences when you are talking about nanocrystals vis-a-vis a bulk crystal when it comes to defects.